welcome back, everybody. So let me hand out the guided notes for you guys. Put them. So these three sections, 8.6, 8.7, and 8.8, are like completely different from what we were doing in the first part of chapter 8. Like in my mind, they are a completely different unit. But why put three sections in a completely different chapter? And they kind of tie in, and you'll see how in a second. But it's something completely different. In my opinion, this is a lot easier than the stuff that we had been doing. Yep.
No calculator.
What? All right. Yeah, did you see it? All right, ladies and gentlemen. So section 8.6 is titled Radical Expressions and Rational Exponents. We're going to be doing 2 days on section 8.6. Honestly, Monday is really just kind of like go over the homework and give you the new assignment. And kind of, I might have to go over this assignment a little bit longer than usual. So Monday we're not learning anything new, just kind of going through section 8.6 again. But it's called Radical Expressions and Rational Exponents. And that's really the only place where it ties into the stuff that we were doing before. You know, sections 8.1 to 8.5 is all rational functions, where the actual function was a fraction. The only similarity between what we were doing and what we're doing now is rational exponents. So think about what that word means. Rational means a fraction, and exponent. So now what we're going to be doing is putting fraction within exponents and seeing what happens with that. And it's really not too bad. It's really not too difficult. All right. We're probably familiar with finding square roots of a number. Probably very familiar, and even maybe familiar with finding cube roots of a number. Finding the square of a number and finding the square root of a number, those are inverses of one another. Similarly, there are roots that correspond to larger powers. Like if I think about x to the third, obviously the cube root is the inverse of the x to the third. But what if I continue that? Is it still inverses? Yeah. X to the fourth, I've got the fourth root would be the inverse of taking something to the fourth power. A fifth root would be taking the inverse of taking something to the fifth power. So, you know, 5 and negative 5 are square roots of 25 because 5 squared is 25 and negative 5 squared is 25. So 2 we could call the cube root of 8. Why? Because if I take 2 times 2 times 2, I multiply it over on itself 3 times, I get 8. Right? 2 and negative 2 are called the fourth roots of 16 because if I take 2 times 2 times 2 times 2, repeated multiplication of 4 times over on itself, I get 16. So the process of taking a third root, a fourth root, cube root is third root, fourth root, fifth root, they don't have any special names. So the process of taking an nth root of a number is just finding a number that multiplies over on itself n times to get to that other value. Okay? We could say a is the nth root of b if a to the nth power is equal to b. If I can take a power, if I can take that base to any sort of power and get that bigger number, that's my answer. That's my nth root. The nth root of a real number, a, can be written as the radical expression n root of a. That n is tucked in the little corner there of the radical symbol, right? That n is called the index, right? When we were working with it before, you know, we could have written, you know, if I take this, that's just the square root of 4, right? You good? You get it. You need to go in the hallway? Yeah. Okay, good. The nth root, so like the square root of 4, we don't even need to write the 2 in. But if we wanted to, we could write it like that. We would never really do that. That's kind of like a extra little piece of notation that we've never really done before. But that's truly what it means. The square root of 4, I could tuck a little 2 in there. So when I tuck a little different number in there, like a 3, that's indicating a third root. And that number is called the index. That number is called the index, in plural indices. Of the radical, and a is the radicand. The piece underneath the radical is called the radicand. Okay, the piece underneath the radical is called the radicand. The index is the thing that's tucked in to the little pocket of the square root symbol, or the root symbol. I should call it a square root symbol. When a number has more than one root, the radical sign indicates only the principal or positive root. If there's only ever a positive sign out there, you are indicating only a principal positive root. Taking a look here at this table, think about odd indexes and even indexes. Odd indexes and even indexes. What do I mean by that? Think about the difference between square roots, fourth roots, sixth roots, eighth roots, and third roots, fifth roots, seventh roots, and so on. If I have an odd index, say a third root, a fifth root, a seventh root, I could only have one real root. Yeah, I only have one possible real root. Like if I take the third root of positive 8, it's only positive 2. It's not negative 2, because negative 2 times negative 2 times negative 2 is negative 8. So when I take the third root of 8, I only get one solution. That's it. Negative 2 is not considered to be a solution, because if I took negative 2 multiplied over on itself 3 times, I would get negative 8. If I had, so it doesn't matter, the radicand doesn't matter whether it's positive or negative. Whatever the radicand is, whatever the number underneath the radical is, that sign of that number is going to be the sign of your root. If I've got an even index, well, then it matters what my radicand is, right? Then it matters what's inside my radical symbol. If I've got an even index, say a square root or a fourth root, and a positive radicand, a positive number inside the root, inside the radical, then there are two real roots. I've got to consider both the positive and the negative, which makes sense. You know, I look at x squared is equal to 9, I got to say plus or minus 3, right? The positive root and the negative root. If it's an even index but a negative radicand, a negative number inside the radical, there are no possibility of having any real roots. The roots would come out non-real. That's like taking the square root of negative 9. There are no real roots. There are two non-real roots, two complex roots. Or negative 16 as the radicand has no real fourth roots, right? Even though 2 times 2 times 2 times 2 does get us 16, since it's negative 16, there's no number to get us to negative 16, only positive 16. If there's a radicand of 0, it doesn't matter what the root or what the index is. There's only one root. There's only one root, and it's always 0. Okay, so let's take a look at this. Find all real roots, no calculators. Now, how would I do this without a calculator? How would I go into my if I don't have my calculator, I can't just plug it in. How do I find the 6 roots of 64? Well, let me remind you of if I had the number 24 and I was reducing down the square root of 24 without a calculator and putting it in simplest radical form, you guys would do this. You guys would say 2 times 12, 2 times 6, and 2 times 3, and then you would buddy up, right? That's the process that you did before, and then you said, okay, well, that's 2 radical 6. The buddy goes on the outside, and the things that are left over go on the inside and multiply back together, right? That's how we did that before. The same thing is going to be true, but instead of buddying up, I need to find things that come together in a group of 6. Why was I buddying up? Well, I was buddying up because I needed to find equal groups of 2, because it was just a square root. That's why it was the buddy system, because I only needed one pair. Because I want these 6 roots of 64, because I want the 6 roots of 64, I'm going to need to find buddies of sets of 6 instead of sets of 2. So let's do that. Let's make our factor tree for ourselves. That's 2 and 32. That's 2 and 16. That's 2 and 8. That's 2 and 4. That's 2 and 2. All right. Well, that means that I've got 2 times 2 times 2 times 2. 1, 2, 3, 4, 5, 6. Hey, look at that. 1, 2, 3, 4, 5, 6. Do you see how I have buddies? I have one set of 2s. Right? I have a 6 set of 2s. So that means that the 6th roots of 64 is 2. However, even index, positive radicand, plus or minus 2. Because isn't negative 2 also a sixth root of 64? Yeah. Let's do that same thing with an odd index. Let's find the cube roots of negative 125. So now I'm going to be looking for sets of 3 when I break it down. Now I'm just going to break down the number here. 5 and 25, 5 and 5. Oh, that's nice. Do you see how I have one set? So it's 5. Actually, it's negative 5, right? How did I know that it was going to be negative 5? Well, the initial number was negative. How do I know that it's not plus or minus 5? Because it's an odd index. If it's an odd index, you don't include the plus or minus. Okay. So it's just negative 5. That's it. What if I wanted to find the fourth roots of negative 81? Could I possibly find the fourth roots of negative 81?
No.
No. Even index, negative radicand. So there are no real roots. Okay? There are no real roots. There are imaginary roots, but no real roots. All right, so let's start looking at some properties about this. Remember the product property and the quotient property of square roots. They're very similar to the product property and the quotient property of nth roots. We're just applying what we know from square roots and saying, okay, what if I change up the index? What if I change up, make it a third root instead of a square root? Do the rules still apply? Yeah, the rules still apply. If I've got the third root of a number, or third root of a product, I can break it apart. And if I've got the same index and I'm multiplying them together, I can multiply them both together underneath the radical and keep the same index. Same thing is true for a quotient. Just like I could, if I had the square root of two different numbers, I could take the square root of the entire fraction. That's fine. If I've got the fourth root of two numbers, I could take the fourth root of the entire fraction if I wanted to. So those rules still apply. Those rules are not new. We're just applying them to bigger indices. When an expression contains a radical in the denominator, you must rationalize the denominator. Okay? Make sure that you're always rationalizing the denominator where you need to. To do so, rewrite the expression so that the denominator has no radicals. So let's take a look here. Fourth root of 81x to the 12. Assume all variables are positive. I have to assume all variables are positive because if the variables turn out negative, or if something happens and turns out negative, wouldn't happen in this case. But then I would have no real roots of anything underneath the fourth root. So I gotta just assume that all variables are positive. All right, 81x to the 12. So here, no calculators. Well, that just means I've got to take, what is that, 9 times 9? So 3 times 3, 3, 3. Look, a buddy set of 4. I'm looking for a buddy set of 4 because that's my index. So this is a 3. Now, what do I do with the x to the 12? So remember, if I had a square root, I would just be taking roots of 2, right? So the same rule applies for a fourth root, but 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so what I'm going to do now is I'm going to take equal roots of 4. So what is the fourth root of x to the 12?
4, yeah. 3.
X to the third.
Is that x to the plus or minus third?
No.
Oh, yeah. Because take the x on.
Now, can anybody think of a shortcut that I could have used?
You divide the 12 by the 4.
Exactly. I divide the 12 by the 4. I divide the index from the power. I take power divided by index. Why is that the case? Well, what am I really doing here? I'm separating my index. I'm sorry, I'm taking separate groups of my index, right? I'm dividing my power into equal groups of my index. So what that truly is doing mathematically is dividing your power divided by your index. Okay, it's always power divided by index. Could you logically reason it through like this? Of course you can, that's totally fine. But you don't really need to. All right, let's take another one here. 4 through to 16x to the 8th over 5. Now remember that I could take, if I've got a square root of a fraction, I could take the square root of each top and bottom piece. Right? So I could take square. I keep saying square root. Excuse me on that. I mean the radical of each top and bottom. I could take the 4th root of 16x to the 8th and divide it by the 4th root of 5. Now, the 4th root of 16x to the 8th, I would be taking the 4th root of 16 and then the 4th root of x to the 8th, right? The 4th root of 16, isn't that just 2 times 2 times 2 times 2? We should start to recognize powers of 2. Right? Those keep coming up again, so please try to start recognizing powers of 2. Like the 3rd root of 8 is 2. The 4th root of 16 is 2. And what's my power on x? 8 divided by 4 is 2. So I got 2x squared in the numerator, and then I've got this 4th root of 5 in the denominator. Now, can I leave a root in the denominator? No, because that's an irrational number. So I have to rationalize the denominator. Now, to rationalize the denominator, before we had said, okay, well then I'm just going to multiply it by the 4th root of 5 over the 4th root of 5. Now, don't do this real quick. I'm just going to show you something here. If I were to do that, I would be taking, well, that would get me 2x squared, 4th root of 5. I can't combine anything in the numerator. And then I would get the 4th root of 25. Did that do anything? Did that truly make the denominator rational? No, because what is the 4th root of 25? It's still an irrational number. It's still a messy number. It didn't work out correctly. So just multiplying it by one set of these does not work. You know what does work?
Multiplying by 4 sets.
3 more. I want a total of however many, whatever the index is. Yeah. See, it's already there once in the denominator. So I want to multiply it by the 4th root of 5 3 more times. That's what truly rationalizes the denominator. How did I know that I want 3 more times? Well, because one was already there and the index is 4. I need 3 more to fill it up. Because now what's going to happen? Well, the numerator is just going to be 2x squared, 4th root of, and now 5 times 5 times 5 is 125. And then divided by what? Just 5, right? Because if I've got the 4th root of 5 to the 4th power, whatever that is, right? 5 times 5 times 5 times 5 is 5 to the 4th. The 4th root of 5 to the 4th is just 5. And that's my answer. Any questions about that? Now, I did want to talk about something. What happens if there's like, this is not on your guided notes, but what happens if there's something like the 3rd root of, 27x to the 8th? What is the 3rd root of 27? Well, that's 3 times 3 times 3. But x to the 8th, what happens if I take 8 and divide it by 3? I get a decimal, right? I get a remainder. So what do I do with something like that? Well, think about it logically. 1, 2, 3, 4, 5, 6, 7, 8. 2, 4, 6, 8, And now let's take equal groups of 3. So I've got this buddy set coming out, this buddy set coming out, and 2 left over, right? Looking for groups of 3. So it's x squared, because I had 2 groups coming out, with 2 left over. Okay? That's how that looks. What if I had changed this number? What if I had said instead of 27, what if I had said 54? What if I had said 54? Well, this would have been 2 times 27, and then that's 3 and 9 and 3 and 3. See, I have a buddy set of 3s coming out, but then there would be a 2 left over, right? So the leftover goes inside the radicand, inside the house. Okay. So the rules that we had for square roots still apply to our bigger indices. All right, let's keep going. So where does this tie into the last stuff that we were doing again, rational exponents? We've already seen that if I take the power divided by the index, that reduces that down. So what I can really do is equivalently talk about radicals as power divided by index. I can really talk about any rational exponent as a radical, any fractional exponent as a radical. A rational exponent is an exponent that contains a fraction in it, where m over n, where m and n are integers. Radical expressions can be written using the rational exponents. Okay? The exponent 1 over n indicates the nth root. That's a really important statement that we say. And actually, this is the more important piece, because that's what we'll usually have. The exponent m over n indicates the nth root raised to the nth power. Power divided by index. Power divided by index. Power divided by index. Okay? If I've got an exponent, say like 8 to the 2/3 power, that means that the 2 is the exponent, 2 is the power on 8, and 3 is the index. So really, I could write that as the 3rd root of 8 squared. Or equivalently, this is commutative, 8 squared, and then taking the 3rd root of that. Right? Both of those things are equivalent. Right? See, this is the statement here. Look, power divided by index. I could put the power outside, or I could put the power underneath. That's commutative like that. I could take the power first and the index, or I could take the index first and the power. It all depends on whatever makes it easier to reduce down the number. The denominator of a rational exponent becomes the index of that. Yeah. All right, so let's take a look here. -32 to the 3/5 power. -32 to the 3/5 power. So I could equivalently write this in 2 different ways. I could say that this could either be -32 to the 3rd power, and then taking the 5th root of that, or taking the 5th root of -32, and then taking the 3rd power of that. Now, which is easier without a calculator? You guys going to try to do 32 to the 3rd power without a calculator? Not me. No, thank you. But can I take 5th root of -32 without a calculator? Yes. I can. You can. Because it's all 2's. 2 and 16, 2 and 8, 2 and 4, 2 and 2, 5 sets of 2's. So this is really -2 to the 3rd power, or -8. Okay? All right, let's keep it going. 64 to the 1/3 power. Whenever you have a 1 in the numerator, you're not changing that number at all. You know, the only thing I could do is take 64 to the 1st power and taking the 3rd root of that. So if you've got a 1/3 exponent, that's taking the cube root of that number. And then the cube root is 64. Well, let's just break down 64. That's 8 and 8. 2 and 4. 2 and 4. 2 and 2. So this gets me 2 times 2 times 2 times 2 times 2. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Okay. Thought I lost count for a second. And then I take equal groups of 3 and I say, okay. So this is equal to, okay, 4. It didn't come out of nowhere. Didn't come out of nowhere. He just pulled a 4 out of nowhere.
I've been kind of thinking that this whole time, but I've just been going.
Okay, so did you see how I did a factor tree for 64?
I've literally been thinking the same thing, Jenny, so.
Okay, are we good with the factorization? So the index is 3, right? So I'm going to take equal groups, equal 3 sets of 2s. So I have 2 of them, right? So what happens there is I take this 2 and this 2. Because if I take the cube root of, this is really like taking the cube root of 2 to the 3rd. And this is really like taking the cube root of 2 to the 3rd. Don't those cancel? So I'm going to end up with 2 2s, which is 4.
I'm confused because,
This fast one?
yeah.
Okay.
Oh, I get it now. Wait, I think.
So we only had one set.
I get it. And so it would have been just 2, but then we multiplied. Okay, I got it.
Okay, we didn't have anything else to multiply it by. Let's try another one. Let's try another one. 4 to the 3/2 power. So there's 2 different ways to write this. Right, Liam?
Yep.
So we have 4 to the 3rd, and then the square root of that. Yeah, you can tuck a little 2 in there if you'd like to. Or you can take the square root of 4, and then take that to the 3rd power. Honestly, both are, you could do without a calculator. Bless you. I'd like to do the square root of 4 to the 3rd power, if that's all right with you guys, because that's a little easy. The square root of 4 is 2. 2 to the 3rd is 8. The other option would be to take the square root of 4 times 4 times 4 would be 64. We just saw that. And then the square root of 64 is 8. You don't even need to write that. You know.
I realized how dumb of a question it
That's okay. No. There are no dumb questions. All right. So let's try to work it backward. We took a fraction and turned it into a radical. Let's take radicals and turn it into fractions to see if we can simplify down a little bit. This is very slick. Like, because if I look at this problem right now, I don't want to try to take 13. Look at this. This is no calculator problem. You mean to tell me I'm going to take 13 to the 4th power? You're crazy. But what I can do is this. Power divided by index. And what can I do? So this is 13 to the 1/2 power. And 1/2 power is square root of 13.
We are on something today. This video is gonna
I go, mice in the background.
tell me I'm wrong.
Yeah, and then that's it. Because that's fully simplified down. You can't simplify the square root of 13. If I tried to break down the square root of 13, it's prime, so there's no buddies to come out or anything.
We try to do the next one on our own.
Sure, why don't you do the next one I know?
He doesn't have any buttons. It's easy, I think. Yeah, that's easy.
Now, just leave it as an exponent. You don't have to multiply it all out.
Wait, what? Multiplication
Oh, okay.
Wait,
what?
Here's what I'm saying. What does this turn into? 13 to the third power.
Oh, why is it 13 over 5? Oh,
Power over index.
shoot, I get it. All right. I get it now.
And I'm okay, we can just do this 13 to the third power. Especially because if this is truly a no calculator, then don't worry about that.
17.
17.
Oh, there's more.
Oh, there's more. But wait, there's more. Now.
But wait.
But wait, there's more. All of this stuff, anything on this page, we had back in the first chapter. All of this stuff is not new. These are all of my exponent rules. What I'm getting here is that you can use your exponent rules with fractional exponents as well, where multiplication means addition, where division means subtraction, where power to power means we multiply. But now we're just going to be working with fractions within an exponent. Here's what I mean. Do you see how these have the same base? I have 7 to the 7/9 times 7 to the 11/9. Isn't that 7 to the 7/9 plus 11/9? You see that? Multiplication of the bases means addition within the exponents. So this is truly 7 to the 18/9 because they already have a common denominator, which is 7 squared, which is 49. See, that simplifies down really nicely. Like, think about if I were to try to simplify first. I would be trying to take 7 to the 7th power and take the 9th root of that. And then taking 7 to the 11th power and taking the 9th root of that. But it all just simplifies down into 7 squared. Division of the like bases means subtraction within the exponents. 3/4 minus 5/4. Now this one's a little tricky because if I take 3/5 minus 5/5, I get negative 2/5, or sorry, 3/4 minus 5/4. I get negative 2/4, which is negative 1/2. Right? Yeah. And what is the negative telling me to do? What's the negative up in the exponent telling me to do? Put it in the denominator. So this is really 1 over 16 to the positive 1/2 power. And if it's a 1/2 power, that's a square root. So 1/4. Remember index? I can write that in there if I'd like. Yeah, at 16 to the 1/2 power. 16 to the first power, putting an index of 2. So that simplifies all the way down to 1/4. And then here's our last one.
Oh, thank goodness.
We don't have to do that word problem.
Woo!
Negative 8 to the negative 1/3 power. So if I take negative 8 to the negative 1/3 power, the negative power is telling you to do what again? Take it into the denominator. So this is going to be negative 8 to the positive 1/3 power. And taking something to the 1/3 power is the same thing as taking that thing to the cube root. And what is the cube root of negative 8? Negative 2.
I was kind of close.
So negative 1/2 or 1 over negative 2 is my answer. Sorry, I forgot to write the homework up there.
Don't write
No,
Is our calculator before?
You might want to stop.
Oh, I forgot something.
Morning, Will.